only the difference is that in electrogravimetric method, the product is deposited qualitatively on an electrode by an electrolytic reaction, and the amount of the product is determined by weighing the electrode before and after analysis. That means, so before analysis, before doing the experiment, you have to take the weight of the electrode, and after the experiment, again you have to take the weight of the electrode. So the amount of the substance deposited can be quantitatively measured, and that is the principle of electrogravimetry analysis. So the material is deposited on an electrode by application of potential instead of chemical precipitation method. In the conventional gravimetric analysis, the material will be deposited due to chemical precipitation from a solution, but here in the electrogravimetric analysis, the material is deposited on the electrode by application of potential. So before learning the principle of this analysis, let us understand some important terms used. So first, before going to the, so this is your long question. Now before going to the long question, that is the principle of this analysis, first we should acquainted with some fundamental terms. So from potentiometric studies, now we will know that what is a cell. Now, so first we will discuss what is the cell. A cell consists of two electrodes immersed in an electrolyte. There are two types of cells. Already we have discussed in the last class. There are two types of cell, that is a galvanic cell and another one is electrolytic cell. And the galvanic cell or voltaic cell and another one is electrolytic cell. So already we have discussed in the last class, that is the galvanic or voltaic cell is a device which converts chemical energy into electrical energy. And similarly, so the galvanic cell or voltaic cell is the device which converts the chemical energy into electrical energy. That means electrical energy will be produced due to the chemical reaction taking place inside the cell. And the galvanic cell usually consists of two types of electrolytic solutions in which the two electrodes of different materials are dipped in it. A particular example of the galvanic cell is the Daniell cell that we have already discussed. So, when energy is supplied from an external source, the cell through which flows is known as electrolytic cell. That means when electrical energy will be supplied from the external source, and after that a chemical reaction will take place inside the cell, that is called the electrolytic cell. So, irrespective of whether the cell is galvanic cell or electrolytic cell, we call the electrode where the oxidation takes place, that is anode, and the electrode where the reduction takes place, that is cathode. Now in the potentiometry, we have already learned that the cathode is assigned a positive sign and the anode is assigned a negative sign. However, in the electrolytic cell, these are the electrodes acquire the charges opposite to that above. That means in the electrolytic cell, the cathode is assigned a negative charge and the anode is assigned a positive charge. So that is the only difference, a technical difference between the electrolytic cell and the galvanic cell. Consider the cell in which type of copper is deposited at the cathode and oxygen is evolved at the anode. So this is the cell reactions, this is the cell representation. You can see in the cell representation the left hand side where copper 2 plus is converted into copper, and in the right hand side oxidation of water taking place so that oxygen will be released at the anode. So at the cathode you can see copper 2 plus by consuming 2 electrons, copper 2 plus is converted into copper 0, and where the metallic copper is deposited on the cathode. And similarly at the anode, water will undergo oxidation to form oxygen. So the oxygen will be liberated at the anode, and the overall cell reaction will be like this: copper 2 plus plus water gives rise to 2H plus plus half oxygen and copper 0, that means metallic copper. So here the metallic copper will be deposited on the cathode while the oxygen gas will be liberated at the anode. So the potential of the electrochemical cell E cell, so E cell equals to E cathode minus E anode. Now Consider the electrolytical cell that is given in this figure. So in this figure you will see that a voltage E applied, that is the external voltage is applied to the cell in such a way that current flows the cell. So when the E applied is greater than E cell, there will be flow of current in the circuit. Where there is a current, the potential of the cell is less than the thermodynamic potential, because one of the following phenomena are operative, that is the IR drop and concentration polarization and kinetic polarization. So here, due to this, so so here first we will discuss what is IR drop, that is ohmic potential or IR drop. So in the electrochemical cells, like the metallic conductors, resist of the flow of the charges in both type of the conduction. Ohm's law describes the effect of the resistance. So the product of the resistance R in a cell in the ohms, the product of the resistance R of a cell in ohms, and current I in amperes, that is called ohmic potential or IR drop of the cell. So that means if the resistance of the cell is R, and if I amperes of current pass through the cell, then the ohmic potential will be IR. So that amount IR amount of potential will be dropped. So that's why that is called IR drop of the cell. We know that when the applied potential E applied equals to E cell, that means the external voltage E applied equals to E cell, then no current flows through the cell. But when we will gradually increase the external applied potential, that is when we will gradually increase the E applied, a small current appears in the circuit, and this current through the cell encounter a resistance of R, resulting a potential drop minus IR volts. In other words, the applied potential must be greater than the theoretical cell potential by IR amount of volt, by minus IR amount of volt. That means E applied equals to E cell minus IR. So E applied equals to E cathode minus E anode minus IR. So where E cathode and E anode equals to E cell are the electrode potential computed in the Nernst equation. So the above can be so the above equation 2.2, that can be rearranged as I equals to minus E applied divided by R plus 1 by R E cathode minus E anode. That means I equals to E cell minus E applied divided by R. Now for small currents and before periods of time, E cathode and E anode remain relatively constant during the electrolysis. So the cell behavior can be represented as the E cathode and E anode are remain constant. So 1 by R into some constant. So this factor will completely become one constant. So the cell behavior can be represented by I equals to minus E applied divided by R plus K, where K is the constant. So this is a plot of the current versus potential. So this figure shows that a plot of current as a function of applied potential in an electrolytic cell should be straight line in the slope having negative slope. So here the slope will be minus 1 by R. So here it will convert this equation into, so this equation in this equation I, the variable parameters are I and E applied. So this equation represent the general equation of a straight line, and where having a negative slope of minus 1 by R. So this is the principle. Based upon this principle, a plot is indeed linear with a small current as in figure. So if the current will be small, then according to the above principle, you will find a linear plot. But when as the applied voltage increases, the current deviates significantly from the linearity. So the galvanic cell behavior is in the similar way. So this is the electrolytic cell. In the electrolytic cell, we will see that. So this is the graph represent applied potential V versus current A. So when the applied potential value will be relatively small, the linearity will be maintained for applied potential versus current. but when the applied potential value will be relatively more, the linearity will be deviated from the behavior of the graph will be deviated from the linearity, and exactly opposite thing will happen in the galvanic cell. So, cells that exhibit non-linear relationship are said to be polarized, and the degree of polarization is given by over voltage or over potential. So here, so this type of non-linearity in this both the graphs you can see this type of non-linearity happened due to over potential, but when the applied potential will be relatively small, linearity will be maintained in this graph. But the non-linearity relationship are said to be polar. So due to polarization, when the applied potential will be more, due to polarization, the non-linearity relationship will be exhibit, and the polarization require the application of potential greater than the theoretical value to give a current of the expected magnitude. Thus, a over potential of minus 0.04 volt is required to obtain a current of 0.6 in the electrolytic cell as mentioned in the figure. So here you can see, so this is the difference, that is minus 0.04 voltage. So hence for the electrolytic cell affected by over voltage, then the equation will be converted into E applied equals to E cell minus IR minus over voltage. So these are the questions. Now coming to polarization. How polarization will be there when the applied voltage will be more or at increased applied voltage. Consider again the situation as what we have discussed in the above figure. If we further increase the E applied, so that means if we increase the value of the applied voltage, the current becomes independent of the E applied. This gives rise to limiting current as shown in figure 2.2. 2.4 you can see, so this is the applied voltage versus current. So when the value of the applied voltage will be less, then linearity will be there, but as the value of the applied voltage increases, then the linearity deviate, the graph deviate from the linearity behavior. So if we further increase the E applied, the current becomes independent of E applied, so that means the current will become constant. So after that, if we again increase the E applied, the current will not change. So that will become constant. From this graph, you can see a constant current will be maintained when the applied voltage will be increased to excess value. So at this situation, the electrode is said to be completely polarized since its potential can be changed widely without affecting the current. Polarization can be conveniently divided into two categories. First one is concentration polarization, and the second one is kinetic or chemical polarization. So due to polarization, the current will remain constant from this graph that we will observe. So here we will discuss what is the different types of polarization. So the first one is concentration polarization, and the second one is kinetic or chemical polarization. First, we'll discuss what is concentration polarization. So, when the ions are discharged and deposited on the electrode as a result of passage of current, what we have discussed in the electrolysis, the area in the immediate vicinity of the electrode is depleted depleted of the ions, and the layers offer resistance to the passage of the current. Again, when the ions are discharged, so when the metallic ions will be discharged, they will be converted into neutral atomic neutral metal atoms. So the neutral metal atoms are solid substances. They will deposit on the electrode. So when the ions are discharged, so the neutral metal atoms are deposited on the electrons. So as a result, the area in the immediate vicinity of the electrode is depleted of the ions, and the layers offer resistance to the passage of current. So when the electrodes are deposited by the atoms, discharge atoms, then these solid atoms will offer resistance to the passage of the current, and this type of resistance due to changes in the concentration of the electrolyte around the electrode is known as concentration polarization. So the concentration polarization occurs when the ions do not arrive at the cathode or the product species do not leave the anode fast enough to maintain the desired current. We have already seen that the reactants are transported to the electrode surface due to three mechanisms. First one is due to diffusion mechanism, second one due to migration of ions, and third one is convection. So the concentration polarization arises when the effect of diffusion, migration, and convections are insufficient to transport the ions at a rate that produce a current of desired magnitude. So if the depleted area in the vicinity of the electrode is not supplied with the ions from the bulk of the solution by increased diffusion or by convection, so the cathode will be assume more and more negative potential as the applied potential is increased. As a result, a back EMF is set up and the current has to be flow and the applied EMF must be sufficiently above the equilibrium potential to overcome the polarization. Hence, the concentration polarization require the applied potential that are larger than the theoretical value, and that is calculated from the equation 2.1. So you can see this is the equation 2.1. So in the equation 2.1, this is E applied equals to E cell minus IR. So the equation 2.1 is E applied equals to E cell minus IR. So here, hence the concentration polarization require the applied potentials that are larger than the theoretical calculated from the. So here applied potential should be larger, what mentioned in the equation 2.1 to maintain a given current in an electrolytic cell. For this reason, vigorous stirring and heating are important in the electrode deposition to minimize the concentration polarization. And the next one is chemical polarization or kinetic polarization. So this type of polarization occur due to changes in chemical nature of the electrode deposition of another metal or due to the coating of the electrode with a layer of gas such as hydrogen or oxygen. The kinetic polarization may also be caused by the formation of films on the electrode. For example, an aluminum anode is liable to be passivated by coat of aluminum on it. So the kinetic polarization is most pronounced in the electrode process that yield the gaseous product. This is known as gas over potential. So the gas over potential depends upon the several factors. So that depends upon the electrode materials used, current density, temperature, pH of the solution, etc. The over potential may be the over potential for many metals are different, and the over potential at a given current density decreases if the electrode surface is rough. Now coming to types of electrogravimetric methods. So these are long questions again. So two types of electrogravimetric methods are there. First one is constant current electrolysis, and the second one is constant potential electrolysis. So first we will discuss the constant current electrolysis. So in the constant current electrolysis method, the electrodeposition is carried out by keeping the current constant. So here periodic increases in the applied potential are required. Here the current is constant. So periodic increases in the applied potential is required as the electrolysis proceeds. That means when the time will proceed, gradually you have to increase the applied potential. Now as shown in the figure 2.5, the apparatus for the constant current analysis consists a suitable cell and a direct current source. So here a 6-volt battery, a 6-volt storage battery can be used for the DC power source, and an ammeter and voltmeter are used to indicate the current and applied voltage respectively. The applied voltage is the cell that is denoted by the resistor. So resistor, and the cathode is usually cylindrical platinum gauge. So here this is the setup for apparatus of constant current electrolysis. So here you can see in the constant current electrolysis. So this is the circuit diagram of constant current electrolysis. So here in the circuit diagram you have to supply 6 to 12 volt of direct current, and here this is ammeter and voltmeter, and here one motor is there, so that platinum anode is there and platinum gauge of cathode. So inside that platinum anode, and so this is the platinum gauge cathode. So now coming to the physical characteristics of the metal deposited, it is important that the deposits produced by the electrolysis. So we know that during the electrolysis, either metal solid substance will be deposited on the electrode or some gaseous substance will be liberated. So the deposits produced by the electrolysis is pure and strongly adherent, dense and smooth, so that it can be that can be washed and dried and weighed without any mechanical loss. So that means the substance that will deposited on the electrode can be easily removed, and that is very pure metal, so that can be easily removed and washed and dried, and you can take the weight also. So spongy, powdery and flexed deposits are like to be less pure and less adherent. So as mentioned earlier in the principal factor, that the influence of the physical characteristics of the deposits are current density, temperature and the presence of complexing agent. Ordinarily, the best deposits are formed at a current density that is less than 0.1 ampere per centimeter square. So after that, the potential changes during the electrolysis at constant applied potential. So consider here, in order to discuss this, we will take a particular example. Consider the electrolysis of copper 2 plus ion in the acidic medium. You can see in this figure. So here we will consider the electrolysis of current copper 2 plus ion in an acidic medium. Initially, the applied potential of the cell is about minus 2.5 volt, which leads to a current of about 1.5 ampere as shown in first figure 2.6a. So here a current of 1.5 ampere will be there, that will lead to so the initial current will be around 1.5, which leads to so that current will exhibit a applied potential of minus 2.5, and the electrolytic deposition of copper is then completed as the potential as this applied potential. That means the applied potential will remain constant. Now as the reaction proceeds, that means as the deposition of copper proceeds, the IR value decreases continuously, and this decrease is due to the concentration polarization at the cathode, which limits the rate at which the copper ions are brought into the electrode surface and thus limits the current. So the decrease in the IR value must be compensated by an increase in cathode potential. Since the cell potential is constant, the increase in cathode potential is shown by a point B by the reduction of hydrogen ion. So that is so when the value of the so this is the curve for the IR drop. So the IR drop will be compensated by increase in cell potential, that is E cathode. And after that we will discuss the constant potential electrolysis. So by controlled potential electrolysis, it is possible to separate two elements whose deposition potential are differ sufficiently. So the potential of the cathode is controlled so that it never becomes sufficiently negative to allow the deposition of the next element. So when two metallic ions are there in the solution, only one metallic ion will be reduced and deposited, but the next metallic ion will never deposit. As can seen from the figure 2.6b, so this one, so here extra applied potential should be given, but according to this figure 2.6b, the potential of the cathode becomes negative, and the co-deposition of the other species begin before the analyte is completely deposited. So that is happening in the previous method, but in this method, the co-deposition of the other species will not possible. A large negative drip in the cathode potential can be avoided by using 3 electrode system as shown in the figure. So in the so here the control potential electrolytic apparatus is shown in figure 2.7. It consists of two independent electrode circuits that share a common electrode and the working electrode at which the analyte is deposited. The electrolysis circuit consists of a DC source of 12-volt battery, a potential driver that permits the continuous variation of potential applied across the working electrode. A counter electrode is generally that is a platinum electrode, and a current meter. The reference current consists a reference electrode that is called SCE, and a high resistance digital voltmeter and the other working electrode. So the electrical resistance of the reference circuit is so large that the electrolysis circuit supplied essentially all the current for the deposition. The current in the reference electrode circuit is essentially zero at this time. So these are the different electrodes. So here you can use mercury electrode also. So now coming to the applications. So the control cathode potential is very useful for separation and quantitative determination of different metallic ionic species present in the solution. First one, the successive deposition of the metals. If we take a mixture of copper, bismuth, lead, cadmium, zinc, tin, that can be determined by successive deposition of the metals on a platinum electrode. First, copper is deposited by maintaining a cathode potential at minus 0.2 volt, and after weighing the cathode, the copper plated cathode is reused to deposit bismuth. So the deposition of copper at the cathode will take place at a voltage of minus 0.2 voltage, minus 0.2 V, and similarly the bismuth, the deposition of bismuth will take place at a potential of minus 0.4 volt, and similarly the deposition of lead will take place at a cathodic potential of minus 0.6 volt. All these three metals are deposited from a neutral solution containing titrant ions which form a complex with tin 4 plus, and that prevent its deposition. So when all these three metals will be deposited, then the solution will become complex so that the SN4 plus cannot be deposited. When the lead deposition is complete, the solution is made more strongly ammonical, and cadmium and zinc are deposited successively similarly at minus 1.2 volt and minus 1.5 volt respectively. Finally, the solution is acidified to decompose the tin tartarate complex. So that means when all the other ions will be deposited in its neutral form, in the solution tin will be remaining in the solution, and that will form a complex of tin tartarate complex. So finally the solution will be acidified to decompose the tin tartarate complex. That means the tin metallic ions which is already formed a complex with tartaric acid, so that can be removed, that can be decomposed, and the tin is deposited at a potential of plus 0.6 volt using a fresh cathode. So here this is a very important application, that successive deposition of different metals will take place at a different cathodic potential. So for different cathodic potential, particular metal can be removed from the mixture of solution. Now coming to simultaneous deposition, a mixture of copper lead can be determined by the deposition of copper in the presence of nitrate ions at the cathode. Lead is deposited as lead oxide at the anode. Now the next application is preparative organic chemistry. If an organic compound can undergo a series of reductions or oxidations, each at a definite potential, it is then possible to reduce the starting material to the desired product by controlling the potential of the cathode during the reduction process. So the type of the electrolytic reduction is much more economical than the chemical reduction process. and where the side reaction produces on the jet. So in the chemical so reaction, definitely some side so reaction will be there, but that is on the jet. So that's why, but as comparative to the chemical so reaction process, if we will undergo for electrolytic reduction process, the side reactions are generally not observed. Now coming to the applications of electrogravimetric methods, the first one is constant current electrolysis. So in this case, the electrodeposition is carried out by keeping the current constant and applied potential is increased periodically as the electrolysis proceeds. And similarly, the another method, that is the constant potential electrolysis. So in this case, the electrogravimetric method is also called, that is a potentiostatic method. So in this method, the potential of the working electrode is maintained at a constant level versus the reference electrode. So this technique required additional equipment like electronic voltmeter, a potentiostat, and a reference electrode. So by constant current or constant potential, electrogravimetric methods have wide application in the quantitative identification of metals and in selective separation processes. We can summarize the application of electrogravimetry. First one is quantitative analysis, that is called electrogravimetry. So that we have discussed, and similarly separation of different ions from a separation of selective ions from a mixture of different ions at different cathodic potential, and simultaneous deposition, and similarly preparative organic chemistry. So these are the applications. Now we will move to the next unit, that is the coulometry. So this is another long question. First we will discuss the basics of coulometry. Coulometric method of analysis are based on the measurement of quantity of electrical charges that passes through the solution during an electrochemical reaction. Again, coulometric methods of analysis are based on the measurement of quantity of electrical charges that passes through a solution during an electrochemical reaction. The principle of coulometric method The principle of coulometric methods of analysis is governed by Faraday's law of electrolysis, that we have already discussed. That Faraday's law of electrolysis, the mass of the substance deposited is directly proportional to quantity of electrical charge Q. So that is M is directly proportional to Q, and again we know that Q equals to current I into T. So that time t second. So M is directly proportional to Q. So that is the Faraday's law, the statement of Faraday's first law of electrolysis. Now M is directly proportional to Q, or M is directly proportional to IT, or M equals to ZIT, where Z is the proportionality constant, and the unit of Z depends upon the unit of the mass and unit of the charge. Now coming to Faraday's second law of electrolysis. So according to the statement of the Faraday's second law of electrolysis is like this: the mass of the different substances evolved or deposited, that is MR, is the molar mass of the substances liberated or deposited, and N is the valency of the number of ions. So here the statement: the mass of the different substance evolved or deposited, if the substance will be gaseous substance, that is evolved, and if that is solid substance, that is deposited. So the mass of the different substances evolved or deposited by passage of same quantity of electricity, that is connected in, so if different cells are connected in series, so same quantity of electricity will pass through the different cells. So the mass of the different substances evolved or deposited by passage of same quantity of electricity are proportional to their chemical equivalence or equivalent weight. That means M is directly proportional to molecular mass divided by N, that is the equivalent weight of the substance. So M is directly proportional to equivalent weight, where M is the mass of the substance liberated or deposited, and Mr is the molar mass, and N is the valency. So Mr by N is nothing but the equivalent weight of the substance. That means M is directly proportional to equivalent weight of the substance. So if M1 and M2 are the masses of the two different substances liberated by the passage of same amount of electricity, and capital M1 and M2 are the respective molar mass of the different substances, N1 and N2 are the respective valence number of the ions, then M1 N1, so M1 is the mass of the first substance deposited, N1 is the valency, and capital M1 is the molar mass. So M1 N1 by capital M1 equals to M2 N2 by capital M2. For example, if we consider two different cells, so in the first cell, same quantity of electricity will pass through the solution of copper sulfate and silver nitrate connected in series. So here the two cells are connected in series. The first cell contains copper sulfate solution, while the second cell contains silver nitrate solution. If the two cells are connected in series, so that same amount of electricity will pass through the two cells. Then the form of the Faraday's second law, that is mass of the copper deposited into 2 divided by molar mass of copper equals to mass of the silver deposited into 1 divided by molar mass of silver. So here why 1 is there, because the valency of the copper is 2, but here the valency of the silver is 1, and hence the quantity of electricity, that is charge, is equals to product of the current and time, that is Q equals to IT. So the practical unit of electricity is coulomb. So when current of 2 ampere flows in 10 seconds, then the quantity of electricity will be 2 into 10, that is 20 coulombs. Now, the quantity of electricity carried out by 1 mole of electron is called Faraday, that is 6.022 into 10 to the power 23 number of electrons into charge of 1 electron, that is 1.6 into 10 to the power minus 19 coulomb, and for 1 mole it is 6.022 into 10 to the power 23. If we multiply both the factors, that will give rise to approximately 96,500 coulomb. So here 1 Faraday equals to 96,500 coulomb. Now consider this reaction Mn plus, that is the metallic ion, plus n number of electron, that will be converted into solid metal. So here the quantity of electricity required for the deposition of 1 mole of element will be equal to Nf, where n is the number of moles of the electrons required for the reaction, and let Mr be the relative atomic mass of 1 mole of atom of an element. Hence the deposition of Mrg of the element, we require Nf, that is n into 96,500 coulomb of electricity. So M equals to Mrq divided by 96,500 n gram. So this much amount of the substance will be deposited, where M is the mass of an element that is deposited by passage of q coulomb of current. So that is M equals to Mr in place of Q, we can write IT. So Mr IT divided by 96,500, 96,500, by mistake it is so written 95,600, but actually that is 96,500, 96,500 N. So this equation is useful for the calculation of mass of an element deposited by the passage of known quantity of current. So here one question is there. Calculate the time needed for a constant current of 0.96 ampere to deposit 0.5 gram of cobalt 2 elemental cobalt 2 as elemental cobalt, that is cobalt 0, at the surface of the cathode. So the molar mass of cobalt is 58.9. So here in this equation, you have to show this question. You have to calculate the value of T. So the value of T you have to calculate. So this one is required. And here the value of M is given, that is 0.5 gram. And the value of I is given, that is 0.96 ampere. And MR value is 58.93. And here the N value is nothing but 2. That is cobalt 2 plus. So by putting all these values, we can find out the time needed for a constant current of 0.96 ampere to deposit 0.5 gram of cobalt 2 plus as elemental cobalt. Now coming to what is a coulometry. So in the first unit or in the previous unit, you have seen that is seen in the electrogravimetry. The analyte is weight as a deposit on of the two electrodes on the electrode. On the other hand, the coulometric methods are based upon the measurement of quantity of electricity. In the electrogravimetric method, we have discussed in the previous unit that the analyte will be weighed. So, so you have to take the weight of the analyte that is deposited on the different electrodes. That is one of the electrode. The amount of the substance deposited, you have to take the weight of the amount of the substance deposited at one of the electrode. So that was the method of electrogravimetry. But here, in the coulometric methods that are based upon the measurement of quantity of electricity, in the electrogravimetric method, you will take the measurement of weight of the substance deposited at any one of the electrode. But in coulometric method, here you will take the measurement of quantity of electricity. In the other word, the quantity of electricity needed to be complete the electrolysis serves as a measure of the amount of the analyte present in the solution. So a coulometer is a device that is used for measuring the quantity of electricity required to bring about a chemical change of the analyte. It is usually practiced in the coulometry to substitute the ammeter with a coulometer. So when a coulometer is a second electrolytic cell, which is the anode and cathode may be the same compartment. So in which the anode and cathode may be in the same compartment or in separate compartment. Suppose to proceed at 100% current efficiency, it is put in series with the electrolytic cell so that the same quantity of electricity pass through both the cells. But here you will measure same quantity of electricity will pass both the cell. So, but here you will measure the amount of the substance deposited at the first electrode. So, various types of coulometers are there. That is the first one is gasometric coulometer. So, here hydrogen oxygen coulometer, gasometric coulometer. One type of gasometric coulometer is hydrogen oxygen coulometer, and the next one is galvanic coulometer. That is the silver coulometer, and the next one is titrimetric coulometer, that is the iodine coulometer. So here we will discuss about the different types of coulometric methods. So first we'll take so before discussing that, we'll take 2-3 minutes of break, and after that again we will continue. So here we will continue now. The first one is gasometric coulometer, that is hydrogen oxygen coulometer. So here the hydrogen oxygen coulometer consists of a glass tube of about 50 centimeter long with internal diameter of 2 centimeter. So here you can see that is a glass tube of 50 centimeter long and internal diameter of 2 centimeter. Two platinum sheets of about 1.5 square centimeter are joined with the stout platinum wire that is served as electrode, and a calibration tube that is a gas burette is connected to the electrolysis tube by means of a pressure rubber and is capable of moving vertically so that adjust of the pressure of the control gas to atmospheric pressure before measuring the volumes of the gas. So this is the gas burette. So here the copper wire, so the two tubes are connected through the copper wire. So a 0.5 m solution of potassium sulfate is used as the electrolyte. So this is the hydrogen oxygen coulometer. And on electrolysis, the following reactions occurs at the anode and cathode. So what is happening at the anode? At anode, the OH minus ion is converted into water and oxygen gas. So that means oxidation takes place here for conversion of water into oxygen gas, and at the cathode the reduction reaction takes place. So the 4 H plus ions, H plus ion will be converted into hydrogen. So the overall reaction is 2 moles of water converted into 2 moles of hydrogen gas and 1 mole of oxygen gas. That means for the 2 moles of water, one water molecule is oxidized to oxygen gas and the another one is reduced to hydrogen gas. So 3 moles of gases, that is 2 moles of hydrogen and 1 mole of oxygen, are produced by consumption of 4 Faraday of electricity, which is equivalent to 0.1741 centimeter cube at entropy of a mixed gas per coulomb. So such a coulometer shows an accuracy about minus 0.1% at a current density of 0.1 ampere per centimeter square, and that is falling to minus 4% at 0.01 ampere per centimeter square, and the loss of efficiency increases as the current density decreases. It has been reported that the loss of efficiency due to the formation of hydrogen peroxide at the anode, which aggravate the situation by being reduced at the cathode, so that the cathodic current efficiency also suffers. So so that another common gasometric coulometer, that is the hydrogen nitrogen coulometer. So here this is the hydrogen nitrogen coulometer. You can see here you will find nitrogen and hydrogen gas will be produced. And similarly, this is the setup of silver coulometer, and the next one is iodine coulometer, and the next one is colorimetric coulometer, then radioactive coulometer. So these are for the short questions. Now we'll discuss the types of coulometric methods. So the coulometric methods are classified into two types. The first one is constant current coulometry, that is called amperostatic coulometry, and the second one is control potential coulometry, that is called potentiostatic coulometry. And again, the amperostatic coulometry is classified into two types, that is primary coulometric analysis titration and secondary coulometric analysis titration. So in the secondary coulometric analysis titration, there will be either external generation analysis or internal generation analysis. Similarly, for control potential or potentiostatic coulometer, you will find the primary coulometric analysis or coulometric analysis. So first we will discuss the constant current coulometer. So In the constant current coulometer, the current is maintained at a constant till the completion of the analytical reaction, which can be detected as a visual indicated solution or by potentiometric method or by spectroscopic method. So that means here the current will be maintained constant throughout the cell, and so that will the constant current will maintain till completion of the analytical reaction, and the completion of the analytical reaction that can be detected by using any indicator or by potentiometric method or by spectroscopic method. Then the quantity of electricity required to attain the endpoint is derived from the amount of the coulombs consumed. So in the primary constant current coulometry, in this technique, the element to be estimated undergoes direct reaction at the electrode with 100% efficiency. But in secondary constant current coulometry, this method having large application and is frequently called coulometric titration. So in the coulometric titration, so this secondary constant current coulometry, that is also called as coulometric titration. So in this coulometric titration, one of the reactant, that is the titrant, is quantitatively produced or generated at the electrode, which is then stoichiometrically react with the analyte ions that to be estimated. So a titration of ferrous ion versus ferric ion is an example of coulometric titration. Consider the oxidation of ferrous ion, that is iron 2, at a platinum electrode will take place. So the oxidation of ferrous ion will take place to ferric ion. So in the constant current electrolysis towards the completion of the reaction, there is an increase in applied cell potential because the concentration of the due to the concentration polarization, the increase in potential causes the anode potential to point where the decomposition of water takes place. So the decomposition of water takes place in the form of water decomposed into oxygen gas, that is oxidation. The water undergoes oxidation into oxygen gas. So here, hence, at the completion of the reaction, the oxidation of iron 2 plus at a platinum anode is not achieved. So the current efficiency for such a process is less than 100%. By introducing excess quantity of the cerium 3 plus, which is oxidized at the lower potential than that of the water. So the cerium 3 plus will be oxidized into cerium 4 plus at a lower potential than that of the oxidation of water. A coulometric determination of iron 2 plus can be achieved by this method. The cerium 4 plus react with Fe2 plus, that is converted into the, here the ferrous ion is oxidized into ferric, and the cerium 4 plus is reduced into cerium 3 plus. So the ferric ion produced by the oxidation of ferrous ion at the anode, that diffuses out and react qualitatively with the ferrous ion, and hence the ferrous ion oxidizes into the ferric ion. So the net effect is the electrochemical oxidation of iron 2 plus with 100% current efficiency. Then the control potential coulometric analysis, or that is called potentiostatic coulometry, and the special feature of the coulometric method. So here these are the special features. And now coming to the control potential coulometry, that is called potentiostatic coulometry. So here this is the principle. So in the potentiostatic coulometry, the principle is like this. In the potential, so the potential of the working electrode is held constant. That's why the name is potentiostatic. That is, the potential of the working electrode will maintain constant. And this technique is also similar to the electrogravimetric method, where the electrolysis is carried out at a fixed potential. However, the former is more convenient than the electrogravimetric method by the fact that the weighing step at the final stage, that should be avoided. Hence, the control potential technique can therefore be applied to the system that yield deposit with poor physical properties, for example, antimony, and to reactions that do not give any solid product at all. For example, the electrolytic oxidation of arsenous acid to arsenic acid at the platinum electrode, that can be takes place. So this is the instrumentation part. So here this is the instrumentation part of potentiostatic coulometry. So first one is the principle, Then the instrumentation part. So these are the instrumentation parts, and then the application. So that can be applied for inorganic analysis, analysis of radioactive materials, microanalysis, multi-step control potential analysis, continuous monitoring of gas streams, electrolytic determination of organic compounds, electrolytic synthesis of new organic compounds, determination of n values of the reaction. Now coming to the constant current coulometry, that is the amperostatic coulometry. So in this method, the technique is better than the coulometric titration. So the technique is known as the coulometric titration method. This technique is known as coulometric titration method. Just wait for some time. So here we will discuss constant current coulometry or amperostatic coulometry. This technique is also known as coulometric titration. So in a coulometric titration, the titrant that is electrolytically generated react with stoichiometrically with reacts stoichiometrically with the analyte and proceeds with 100% of efficiency. It involves the single chemical change in the analyte. So that means here the titrant that is electrically generated react with the analyte and the reaction takes place stoichiometrically. Stoichiometrically that will react with the analyte, and here only a single chemical reaction will take place. So that's why this method is 100% efficiency, proceeds with 100% efficiency. The coulometric titration has a special advantages in the sense that standard solution is not required here because the stoichiometric reaction will take place inside the cell. This method is very useful for estimation of micro and semi-micro quantities of substances. So this is the schematic of a coulometric titration method. So this one is magnetic stirrer, and this one is the steering bar, magnetic bead, and here mercury cell, mercury electrode is there, and here inside, so the constant current source will be connected to the two electrodes. This one is the counter electrode containing electrolytic solution. So the figure depicts the principal component of a typical coulometric titrator, a source of constant current that is amperostatic and a switch that is simultaneously initiate the current and start certain electronic timer are required. The potential drops across the standard register, that is R start, is used for the measurement. Many electronic and electrochemical amperometers are available in the market. So this is the cell assembly. So this is a typical coulometric titration cell. This is the assembly of the cell. Then external generation of the titrant. So what is happening inside that? And here this is the detection of endpoint in the coulometric uh, titrations. So that can be takes place with the help of indicator, or also that can take place spectrophotometrically. So this is the spectrophotometric endpoint. And coming to the application of coulometric titration, that can be applied for neutralization titration, for precipitation and complex formation titration, oxidation reduction titration, that is the redox titration, and advantages of the, so these are the advantages of the coulometric titrations. Now we'll move to the application of coulometry. So in the detailed theory, instrumentation and electrolytic cell have been discussed. So the basic relationship used for calculating the amount of the substance, so this one, that is M equals to Mr into Q divided by 96,500 into N. Mr is the relative molar mass of the substance to be electrolyzed, and N is the valence electrons, the number of valence electrons move that involved in the electrode reaction process, and M is the mass of the substance produced or consumed during the electrolysis process, and Q coulomb, Q equals to IT, where I is the current in amperes and T is the time in second. Basically, the coulometry of two types are similar to electrogravimetry. So the two similarity between the coulometry and electrogravimetry is that coulometry with control potential of working electrode and coulometric analysis with constant current, both are similar to electrogravimetric methods. Then application of the coulometric method. So this is the separation of nickel and cobalt by control potential coulometer. So this is the one of the application, that is separation of so that is very difficult by chemical methods. So this is, by this method you can easily separate nickel and cobalt by control potential coulometric method. Then we will move to the next module, next unit. So after that we will move to block 2. That is the block 2 contains three modules, that is voltammetry, polarography and amperometric titration. So that we will discuss on Monday. Voltammetry, polarography and amperometric titration.